We talked about Green's theorem. In fact, we talked about Green's theorem last time, and we said there's this beautiful Stokes theorem, which is a generalization, almost a very literal generalization, saying, oh, you know, I can think of a region in the plane as sort of a region in three-dimensional space. Well, let me just think of different regions in three-dimensional space as being surfaces, and there's Stokes theorem, once you have it properly stated. Now, there's a slightly different variation of Green's theorem. Now, why do we say it's slightly different? You'll notice that this is an n. Last time we had a t. But it's not hard to go from one to the other. So what does this say? If I have a region in the plane here, call my region R, and I look at f dot n, well, what is it it's looking at? So since we're talking about Green's theorem, we should shade it green. So there's a little bit of green. So the n here means the normal, and it means outward normal. So we have an outward normal. So as we move along the curve, there's different directions it points. It just depends on where you're at in the curve. So here I have these various outward normals. Now, what is f? Because the n is associated with the boundary. What is f? F is a vector field, which we can think of as flow. And so, in particular, I have this vector valued function, which is full of little tiny arrows, which point and saying how things are going. Now, of course, arrows can shrink and they can turn depending upon where you're at. And the question becomes, when you're asking what's going on, f dot n, what you're asking for is what's happening with this vector field. In particular, if we think of it as a flow, how much is flowing? So here, the question basically is, how much crosses through your boundary? What's the flow through the boundary? Turns out we can relate it to something happening on the inside. So if I want to know what's happening at the boundary, as far as what's coming in and out, I say, well, look on the inside at the divergence. And divergence is essentially the idea of saying, what's happening locally? Is it compressing or expanding? And so if you know either one, you know the other. So how do we go to three dimensions? And the answer is to say, sort of intuitively. So now we go up to three dimensions. We have our three-dimensional objects, which for me almost always take the form of bean shapes. So here's my three-dimensional bean, and it's a solid. So it's not just a surface, it's a solid shape. And now I can again talk about the normals. So the normals are what? Well, they're going to point out. So since it's a solid, I can imagine actually going and standing on it and saying, okay, what can I say about the orientation? So here, when we talk about n, it's the normal that points out from the solid if you were to stand on its surface. So this f dot n dsa, this is a flow. It's flux. In fact, if you go back to what we talked about fluxes through surfaces. The only difference about this surface compared to what we talked about previously is that our surface here is now closed up. There's no edge because the surface is containing a solid inside of it. So this is sort of a surface without boundary. But other than that, we can still talk about the same type of flux integrals that we talked about before. So I say, if I want to know what's happening through the boundary with this flow, I can answer that by looking at the interior of divergence. And that's the divergence theorem. It's a beautiful thing. So flux through the boundary is found by integrating divergence in the interior. Works in 2 dimensions, and it works in 3 dimensions. And that's it for the theory. The rest of today is practice. So just remember, we're going to see lots of divergence. And one of the reasons why we like divergence, by the way, is it's a lot easier to work with divergence than it is to work with curl. And curl is messy. Divergence is pretty easy. So as a reminder, in case you've forgotten, when we talk about the divergence of f, that's also noted as del dot f. Well, that's just, you take the partial derivatives and add them. M sub x, n sub y, P sub z. So when you talk about the divergence, it's a very straightforward thing to work with. So we're going to try to do a bunch of examples, and let's see how far we get. Let G be the surface of the sphere of radius 1 centered at 0, 0, 0. So centered at the origin. The normals are pointing outward. Find the integral over this surface of 2x, yz, z squared dot n dsa. Now, I suppose I should start by asking, what tool should we use? Well, what tool should we use? Yeah, we should use divergence. How would you crack that code? Well, that's the only thing we talked about. That's a good way to crack it. But there's other things that are good to point out here. First off, it is a surface, but it's not just any surface. It's a closed surface. It's a surface of a solid. In this case, it's the surface of a sphere. So I say, all right. So I can think of this here as my G is the surface of this sphere here. But I can really say, look, G, it's the boundary of a solid. And that solid is the unit sphere. So instead of trying to go through and work out, okay, if we were to do this without our divergence theorem, we could do this question. What would we do? We would say, let's take the top half of the sphere. Let's compute flux through there. Compute the bottom half. Compute flux through there. And the reason we split it in two parts is we could say the top half would be z equals the square root of 1 minus x squared minus y squared. The bottom half would be z equals minus the square root of 1 minus x squared minus y squared. So we can actually do this with our tools. It just sounds like a lot of work. And our goal is to not do a lot of work. We're very pro, let's not work hard. So instead, we say, okay, we can interpret this as the following. This is going to be equal to, my divergence theorem, which we'll just abbreviate here, the triple integral over our solid, I'll call our sphere S, of the divergence of this vector valued function. 2x, yz, z squared. All right, well, this is the triple integral of, now we compute the divergence. Derivative of 2x with respect to x, 2. Derivative of yz with respect to y, z. Derivative of z squared with respect to z, 2z. 2z or not 2z? That is the question. Now, we can really break this up into two parts. One is the integral of 2. So I have 2 integral dv. Then plus 3 integral, because I have z plus 2z makes z dv. All right, now one of these two integrals is pretty easy, and the other one is also pretty easy. Which one do you want to tackle first? The easy one, right? Well, let's start with the first one. How do you interpret the integral of just dv? What is it you're finding? Finding volume. So, if I have a way to find volume without doing the integral, I don't have to do the integral. Do I know the volume of the sphere of radius 1? So the volume of a sphere is 4/3 pi, and then r cubed. In our case, radius 1, so 1 cubed. Okay. Now this integral is not always easy, but sometimes you can look for things. In our case, is there anything that makes it easy for us? Yeah, there's some symmetry here. Now the sphere is ultra-symmetrical. And so what I mean by that, you can go almost any plane that passes through the origin, it's symmetrical about that plane. And in particular, if I take a point that's above the xy plane, and I compare it with a point below the xy plane, and I look at the values, it'll have the same magnitude, but different sign. Because in one point, I'll have positive, the other one I'll be negative. So when I add them all together, what happens? You get cancellation, which means that this integral is 0 by symmetry. Now, if you don't know that the integral is 0, go ahead and work it out. You'll still get the right answer. So our final answer is 8/3 pi.
And so if you did go ahead and work it out, what would your bounds be?
Well, you could set up an integral. I would recommend spherical coordinates because sphere. It's a good dead giveaway. So your bounds would be 0 to 2 pi for theta, 0 to pi for phi, and 0 to 1 for rho. All right. So, given f, which is x cubed plus tangent 1 over 100 yz in the I direction, y cubed minus e to the xz in the j direction, and 3z plus x cubed in the k direction, and a solid, where our solid is x squared plus y squared less than or equal to 4, and 0 less than or equal to z less than or equal to 3. Find the integral on the boundary of our solid, f dot n, dsa. And on a side note, n points outward. Well, n will always point out when you have solids. Now, one of the key words I'll try to direct your attention to is the word solid. When you see solid, you should be thinking, this sounds like a divergence theorem question, because the divergence theorem is built off of solids. It's one of the few things that we have. Now, not everything has to, with the word solid, has to be a divergence theorem. If we say find the mass of the solid, that's not a divergence theorem. But certainly, if you see a solid and you're doing an integral on the boundary, you're thinking divergence. Let's think about our shape. X squared plus y squared less than or equal to 4. What would that look like? Be a cylinder. Now, in the xy plane, of course, it's a circle, but we're in 3 space. So in 3 space, that would be a circle that's been copied up and down. So it's a cylinder. So it's a cylinder that goes all the way up and all the way down. What's the radius? 2. Yeah. Now, we're told that 0 is less than or equal to z is less than or equal to 3. Well, that says we don't keep the whole cylinder going up and down forever, but rather we start where z equals 0. So we start here in the xy plane. This is the bottom of the cylinder. And then we're going to go up to where we have z equals 3. So here's z equals 0. Here's z equals 3. So it's the cylinder. The height of the cylinder is 3. And the radius of the cylinder is 2. So there's our solid. Now, if we were going to compute the flow through the surface, we'd have to say, okay, what's the flow through the bottom? What's the flow through the top? And what's the flow through the side? But that sounds like work. We don't want to do work. We want to be smart. Be smart, do less work. So the question becomes, how are we going to be smart? How are we going to avoid having to do more work? Well, what should we use?
Divergence theorem.
Yeah, let's use divergence theorem. Sounds like a good tool. So, according to our new wonderful tool, that's the integral over the whole solid of, well, let's do it. What's the derivative with respect to x of the first entry? 3x squared. Derivative with respect to y of the second entry? 3y squared. Derivative with respect to z of the last entry? 3. All right, dv. Well, now we have to start thinking, how do we actually do this integral? We should practice. So, looking at our picture, how should we approach this? Cylindrical coordinates. What's suggestive that we should use cylindrical coordinates? Cylinder, yes. If you see a cylinder, you think cylindrical. In general, if you have rotational symmetries, cylindrical coordinates are fantastic. All right, so we're going to switch to cylindrical coordinates. So this is going to equal to a triple integral. 3x squared plus 3y squared plus 3, well, x squared plus y squared becomes r squared, so 3r squared plus 3. Cylindrical coordinates, dv, r, dz, dr, d theta. And now we look at the picture. Theta, that's how much we spin around. In this case, we spin all the way around, so 0 to 2 pi. R is how far out we go. That's the radius, so that's 0 to 2. And z went from 0 to 3. So now we see, okay, this is a nice integral. Everything breaks up. In fact, we can really split this into 3 integrals. So we have the integral from 0 to 2 pi of d theta. We have the integral from 0 to 2 of 3r cubed plus 3r dr, multiplying the r through. And then we have the integral from 0 to 3 of dz. So the first and last integrals are pretty automatic. We don't really have to put much thought into them. The middle integral, we have to put a little bit of thought. What's the integral of 3r cubed plus 3r with respect to r? 3/4 r to the 4th plus 3/2 r squared. Evaluate from 0 to 2. 0 is nice. You get 0, plug in 2. 2 to the 4th is 16. Divided by 4 makes 4. Times 3 makes 12. 2 squared is 4. Divided by 2 makes 2. Times 3 makes 6. So that makes 18. So we get 2 pi times 18 times 3. 18 times 3 is 54. And if we double that one more time, we get 108. 108 pi. And there you go. As they say, Bob's your uncle. Not a lot of people say that nowadays. But if you go back and watch Mary Poppins, and I'm talking old school Mary Poppins with the offensive English accent, then you'll hear the phrase, Bob's your uncle. All right.
So in the previous example there, was F a vector field?
Was f a vector field in the previous example? Yes, it's a vector valued function because you can see the I, J, K. So that's what's happening in the first component, that's your second component, that's your third component. But you can write vector valued functions in multiple ways, so you should be comfortable seeing them in all possible ways because you never know. You want to be adaptable and say, aha, I know how to write it. All right, let Q be the solid consisting of points satisfying x squared plus y squared plus z squared less than or equal to 4, and z is less than or equal to the square root of x squared plus y squared. All right, well that's a solid of some sort. Find the integral on the boundary of the solid of something dot n. N points outward. Now, one of the things I should point out is you're thinking, you keep going in one direction. You're always like, here's the integral on the boundary, and then you always switch to the integral over the interior. Do you ever go the opposite direction? Do you ever say, like, here, let's do this three-dimensional integral on the boundary. Let's do a surface integral instead. And the answer is no. Surface integrals are hard. We like triple integrals. They're easier to set up and to work through. So we almost always use divergence theorem in one way. We have an integral on a closed surface, and boom, we go into the solid that it's enclosed. So, what does this shape look like? Can we recognize some things? X squared plus y squared plus z squared less than or equal to 4. If you just saw that, what do you have? It's a sphere. Yeah, we're getting pretty good at recognizing spheres. Okay, and it's less than or equal to, meaning we're on the inside. Okay, so that's that part. What about z less than or equal to the square root of x squared plus y squared? What does that look like? What is it? It's not a cylinder.
Parabola?
It's not a parabola. If the square root weren't there, it'd be a paraboloid. It's a cone. It's a cone. And it looks something like that. Now, of course, it keeps going up forever. Where do we want to be in this cone? Because we have an inequality. Do we want to be above it or below it? Below it. So we're down below. Down here. Now, you do that very fancy thing called crossing your eyes, and you put them together, and we say, well, what's the resulting shape? Well, the resulting shape is something that looks like this. You're the sphere, except you scooped a cone out of the top. So that's your shape. That's your shape. Okay? Something like that. All right. Well, interesting, slightly different shape, but we like slightly different problems. In fact, that's what makes tests so fun. There's always something new to look forward to. All right. So, let's see. Now we'll apply divergence theorem. By this time, I think we know how to start. Take the derivative with respect to x of the first entry. What do you end up with? Y squared. Take the derivative with respect to y of the second entry. What do you get? X squared. And take the derivative with respect to z of the third entry. C squared. Now, one of the other things that you should learn to recognize is if you see really terrible functions, you should be like, boy, that looks like something I don't want to mess with. And you don't. So, as an example, this e to the y plus cosine y, that's a terrible looking function. You wouldn't want to have to actually work with it. But we don't have to, because it goes away. And so, if you do see things that look bad, you should think, I should find something that makes that go away, so I don't have to work with it. Now, how do we actually do this integral? Spherical coordinates. What suggests spherical coordinates? Yeah, it's a sphere. It's a sphere with something dug out of it. There's other pieces as well. For example, y squared plus x squared plus z squared. What will this become? Rho squared. Now, we should take a second here to talk about our bounds. So we're going to have an integral, integral, integral. Our function becomes rho squared dv, rho sine of phi, d rho d phi d theta. Good. We'll always remember that one. So if I want to understand the bounds, what I like to do is imagine slicing the shape. So I'm going to slice the shape. And if I slice the shape, what will I see? Well, I really just need to focus on one side. This cone is a nice straight line, and then I have this circle coming through. So that when I slice, what I've really done is I've basically done a rotation of this region here. So I need to decide a couple of things. First off, the theta bounds. Well, the theta bounds deal with how much you rotate. So how much do we rotate? 0 to 2 pi. We're going to rotate all the way. 0 to 2 pi. Now, let's do phi. Phi is the angle coming off the positive z-axis. So phi equals 0, point straight up. I'm not hitting anything until I hit this line. Well, which angle is that? Pi fourths. And then I'm like, okay, I see the region, I see the region, I see the region, and I stop once I go straight down. What angle is that? Pi. And I wrote pi halves, but I should have written pi fourths. Pi fourths, and I stop at pi. So pi halves is over here. And I'm hitting the region there. All right. So the bounds for phi, pi fourths to pi halves.
How do you know it's pi fourths? Because the drawing's not exactly a scale.
Are you saying I'm a bad artist? Look, I may not love an art history majors, but that doesn't mean I'm a bad artist. Well, really what I'm going off of is I'm keying off of this. So this line here, what I like when I draw this region, what I'm really drawing here is I'm drawing R and Z. And so this is Z less than or equal to R. So this line is the line Z equals R. So I see Z equals R, that's like Y equals X, that's going off at 45 degrees.
So why is it pi halves?
Where? Oh, because I copied wrong. That's why it's pi halves. Thank you. Double check your work. It's easy to make a mistake. All right. Now, the last part is rho. Now, rho says, how do you come out from the origin? So if I'm at the origin, I go out until I hit a surface. Well, I'm always hitting the same surface. It's that sphere. So what is this surface in terms of rho? Rho equals 2. And I'm going to start at rho equals 0 because I start at the origin. And so I go from 0 to 2. Now, once this is set up, we say, these are beautiful numbers because they're all numbers. There's no functions in these bounds, which means we can break it up. So we get 0 to 2 pi d theta, whatever that is. Then we're going to get pi fourths to pi of sine of phi d phi, whatever that is. And then integral 0 to 2 of rho to the fourth, d rho. So the first one, 2 pi. That's pretty much a freebie. Integral of sine? negative cosine. Evaluate from pi fourths to pi. Well, cosine of pi is negative 1. So minus 1 makes 1 minus cosine of pi fourths root 2 over 2. That's one we should know. Okay. Integral of rho to the fourth d rho. 1/5 rho to the fifth. Evaluate from 0 to 2, which makes this 1/5 times 32. When you plug in 0, you get 0. So, let's see, what do we end up with? Well, I can simplify if I take the 2 and multiply it into there, because I have the 2 in front of the pi. So I'll have the pi, then I'll have 2 minus root 2, and then I'll have 32 over 5. That looks pretty good. All right. Well, we're making decent progress. Yes? Did I? It should be plus, because I am subtracting a negative. Oh my gosh. Well, I still get a sticker. Yeah. Small mistakes. You never outgrow small mistakes, but you get fewer and fewer as you practice. All right. Let t be the solid. 0 less than or equal to z less than or equal to 1. And x squared plus y squared less than or equal to 1 plus z squared. Ooh, this is fun. This is good. N is the outward pointing normals to the bounding surface. We're calling the bounding surface G. Find the integral on G of a crazy expression. Okay. Well, by this time we know crazy expressions, bounding surface to a solid. We go to the integral over the solid, which we're going to call T. We take our divergence. And remember with divergence, it's always you're adding up your partial derivatives. So you should end up with a sum. There should be no more vectors after you do your divergence. Derivative of the first entry with respect to x, 0. Derivative of the second entry with respect to y, 0. Derivative of the third entry with respect to z, 8z. You got to have something. You don't want to end up with having a divergence of 0. We actually had that once on a final. Not on my watch. That's not going to happen. That was back in the old dark ages. Okay. So now that's it. We just have to integrate that. Well, what is our surface? Now this one might be one that you may or may not recognize. Does anybody know what that looks like? It is a hyperboloid. Yeah. So what does it look like? Well, if you think about it in terms of circles, because oftentimes when you see x squared plus y squared, you think a circle. You can say, well, when I'm at z equals 0, I have a circle radius 1. As z increases, my radius increases. So what's happening is down here in the xy plane, I have a circle radius 1, and as I move up, I move out. So that my shape looks something like that. Okay, so here is my t. And I don't go very far. I go up from z equals 0 to z equals 1. All right. So we have to integrate. How do we do that? How do we integrate this shape? That's a good one. That's a good thinking one. How do we do that? Well, which coordinate system should we think about? Cylindrical. Cylindrical is sort of the coordinate system to go to. Now you might say, but it's not a cylinder. That's okay. You can use cylindrical coordinates for things which aren't cylinders. The key for cylindrical is really this notion of rotational symmetry. Whenever you see that rotational symmetry, it's great for cylinders. Great for cylindrical coordinates. And we have that going on in this problem. So once you know you're going to rotate, the next thing to do is say, well, let's just understand what's happening in a slice. And if you look in a slice, what you see here is you start at 1. You're going to go up to root 2, and we're going to go to 1. And we're doing that. That's what our slice looks like. Now, in case you're saying, how in the world did you get root 2 involved in this problem? The answer is I plugged in z equals 1 over here. When you plug in z equals 1, you'll get 1 plus 1, which is 2. So it's a circle of radius root 2 at the height 1, which is where we're stopping. So that's where we're going. All right. So that's what we look like in a slice. And when I talk about a slice, again, I'm talking in the RZ plane. Now, at this point, we have to do something a little bit different than what we normally do. Well, we don't have to. But let's talk about our cylindrical coordinates. Generally speaking, when we do cylindrical coordinates, we have a default. R, dz, dr, d theta. That's the default. It's a great default. But it doesn't always mean it's the best in all situations. Hinting at, there might be a better thing to do in this situation. If we stayed in this coordinate system, we'd run into a small, annoying detail. Namely, when r is small, below 1, I'm just going from 0 to 1. But when r gets past a certain point, when I'm between 1 and square root of 2, I actually go not between 0 and 1, but between this curve here to 1. Which means if we were to integrate in the order dz, dr, d theta, we'd have to split our integral into two parts because the lower part changes. Two integrals is twice as much work as one integral. So we'd like to get one integral. So is there a way to get one integral? Change the order. So the d theta doesn't really matter. We'll put that on the end. We can do dr dz d theta. Now you might say, are you allowed? Yes, we're professionals. And I'm including you. You're graduating from this Calc 3 class in the near future. You're a professional. You know calculus. So you got to pay attention though. So here we go. Integral, integral, integral. We need to update our function. 8z, because we started with x, y, z, which means we were in Cartesian coordinates. But 8z in cylindrical coordinates becomes, that is correct, 8z. R is still r. And we said dr, dz, d theta. Theta says how much we spin. How much do we spin? 0 to 2 pi, all the way. Z. Well, where does z go between? 0 and 1. We can see it in a slice. We just have to focus on a slice now, 0 to 1. Now we get to r. Okay, where does r go from? Well, now we're thinking, as we're slicing it, we're going from left to right. So the bottom bound is 0. Now we got to talk about this other bound. Well, here, go back to your equation. It comes from x squared plus y squared, which is r squared, is 1 plus z squared. Now, I'm doing an r integral, which means I need to write this in terms of r equals something. Well, that's good news. I solve for r. That means it goes to the square root 1 plus z squared. All right. Now, this is an integral you can't pull apart because you have a function in your bounds. That's all right. We can do that. We can do them one layer at a time. It's no problem. Integral 0 to 2 pi, integral 0 to 1. Here I'm integrating first with respect to r. So if I do that, that'll be r squared over 2. So that'll leave us with 4zr squared evaluated from r equals 0 to r equals the square root of 1 plus z squared dz d theta. And now, when you plug it in, the good news is that square root is going to go away because it's r squared. So integral 0 to pi, integral 0 to 1 of 4z times 1 plus z squared. And then dz d theta. Now, of course, we can actually break it up into pieces. So we can say, well, this is integral 0 to 2 pi d theta. And integral 0 to 1, distribute through, of 4z plus 4z cubed dz. Integral 0 to 2 pi of d theta, that's easy. We can do that one. What's the integral of 4z plus 4z cubed? 2z squared plus z to the fourth. Evaluate from 0 to 1, we end up with 3. 2 plus 1. Times 2 pi gives us our final answer of 6 pi. So, 6 pi. That's not so bad. Yeah. Good. Good. All right. Let's try another one. Okay. Let E be the solid region bounded below by the cone z equals square root of x squared plus y squared, and above by the inverted cone, also known as the upside down cone, z equals 4 minus the square root of x squared plus y squared. And let S be the surface, if you like, the boundary of this with outward pointing normal vectors. Find the flux through S of the field. All right. Now, what tells us that we are in a divergence theorem problem? Because there's no integrals here. What's the clue? Or what are some clues? Okay, the fact that we see a boundary of a solid, and what else? The flux. So flux through the surface here is just shorthand for saying that means I want to integrate through S of f dot n, the surface area. So there's keys here that we can see that, okay, this really is a divergence theorem problem. Now, we're not going to compute the flux directly. We're going to use the theorem. So what do we have? Well, we have that the integral over our surface f dot n dsa is equal to the integral over our solid of the divergence of f dv. That's just writing down the tool. Oftentimes, that's like 1 point on an exam. You know, get the 1 point. Preferably get 10, but you've got to work your way up. What's the divergence going to be? Well, derivative of the first entry with respect to x, 0. Derivative of the second entry with respect to y, x squared. Derivative of the third entry with respect to z, 0. All right, x squared. Well, that's not so bad. We just have to figure out now, what does E look like? Well, let's talk about E. It's two cones. So you have a cone, square root of x squared plus y squared. And we've talked about this cone before already today. That's a cone that's coming up. So it's coming up. So there's this cone. But then we have another cone, because it says it's a cone, 4 minus square root of x squared plus y squared. So what you've done is you've turned the cone upside down and shifted it up so that it starts at 4. So maybe let's say this is 4. And what's happening is this cone is going down. And what do we want? Well, we want the things which are sort of in between the two cones. So between two cones. So what we're going to end up with is this shape here. So that's our region. All right. Now, how do we actually go about doing this integral? Cylindrical. What's the key that shows you cylindrical is a good idea? Well, cones. Well, spherical works great for cones too. What I like to key off of is that rotational thing going on. When I see a nice rotational spinning and there's not a sphere involved, I tend to lean towards cylindrical. If I see a sphere, I say, let me see what sphere it is. I might want to do spherical. Now, looking at the slice here in our ZR plane, what we'll see is this becomes Z equals R, and then this becomes Z equals 4 minus R. So if I have Z equals 4 minus R, Z equals R, where do they intersect? Yeah, they intersect at 2. That might be a useful thing for us to note. All right, so we're almost there, almost there. So we're going to switch into cylindrical coordinates. Integral, integral, integral x squared becomes r squared cosine squared, because x is r cosine theta, and dv, well, that's r dz dr d theta. Now you might say, wait a second, you forgot to do something. Shouldn't you use symmetry? And I said, okay, well, can we use symmetry? Now symmetry is helpful if we can get cancellation. Now before we did symmetry, we said, oh, we like had z and negative z, and they cancel out. But now, because of that square, if you look, see, one time it's x squared, but if I flip across, it's still the same. There's no cancellation. So this is not a, aha, 0 by symmetry. This is a, oh, we get to work. Yay! Good for us. Okay, now let's do our bounds. Where does theta go from? 0 to 2 pi, all the way around. Okay, we won't always do all the way around, but oftentimes we like pictures like this. Where does r go from? 0 to 2. Because we talked about we go till we intersect. And where does z go from? R to 4 minus r. So you come over here to the picture. So here I have an r. I start at r, and I go up to 4 minus r. So that's where I'm going in between, is those two. Well, that's not so bad. One thing you'll notice is there's no z involved, so that's easy to do the first layer. Integral 0 to 2 pi, integral 0 to 2, r squared cosine squared, z, evaluated from r to 4 minus r of dr d theta. And I really should, of course, say z equals r to z equals 4 minus r.
Well, why didn't we split them up this time?
Because I have variables in the bounds. So when I have variables in the bounds, don't split them up. Don't split them up. Now, when you evaluate, well, I'm going to get with 4 minus r, which means that I'm going to get 0 to 2 pi, 0 to 2 of r squared cosine squared theta, 4 minus r, or also known as 4 minus 2r dr d theta. Now we can split them up. All right, so if we split them up, what would we have? Integral 0 to 2 pi cosine squared theta.
Where did the r from dz dr d theta?
There we go. It's there. It's just, my handwriting is so bad, my 3's often look like 2's. So, yep. Okay. It's like some of the handwriting of the people who grade the exams. It's kind of weird because, you know, I know they're professionals, but just on a side note, I'll see professors, you know, people with PhDs, and this is how they write their 9s. And what? That's not a 9. Yeah. Okay. That's not even the worst of it. Okay. All right. So, anyways, back to our problem. Okay. The other part with the r cubed there, you multiply it through, then we're going to get the integral from 0 to 2 of the 4r cubed minus 2r to the 4th dr. How do you integrate cosine squared? Power reduction. So really you say cosine squared is 1/2 plus 1/2 cosine 2 theta before you integrate. So when you integrate, you get 1/2 theta plus 1/4 sine of 2 theta. And you're going to evaluate that from 0 to 2 pi. And if you evaluate that from 0 to 2 pi, the nice thing is sine of 4 pi and sine of 0 are 0. So you end up with the first term is pi. Now the second one. What's the integral of 4r cubed minus 2r to the 4th? R to the 4th minus 2/5 r to the 5th. And then we're going to evaluate from 0 to 2. Well, 0 is easy. Plug in 2. You're going to get 16 minus, well, 2/5 r to the 5th. Well, okay, 2 to the 5th, that's 32. So that's 16 minus 64/5, I believe. 2 times 32, 64. That's true. 16, by the way, is also known as 80/5. minus 64 fifths, giving us a total of, from the second part of 16 fifths. And put those two together, and our final answer is 16 fifths pi. Now, if you ended up with a negative, does that mean you did something wrong?
No.
No. You can't have negative flow. You can have positive flow. You can also have zero flow. So it's okay to end up with a negative answer. And looking at our time, I think this is a good place to stop for now.